Let's have a quick look at our first decision tree in R. Before we start this, just a few things. I won't be giving out these R notebooks, there's not much point. I just want to quickly demonstrate to you what a decision tree looks like and the kind of things we need to do to build one carefully. The other thing I wanted to point out is that I had a bit of difficulty in getting the R kernel to work with the Jupyter notebook on my local machine. So rather than waste time, I just found the standard Jupyter image, which they provide as a Docker image. And it was then really quite simple to download that image, start a container, and here I am in that container. You can see that I happen to be at port 10,000. You don't need to be familiar with R to follow along. I'm just installing one package here to plot the trees and setting up some directories. O2B df-all CSV is the Amy's data, removing some columns which we're not going to use and putting sale price into thousands, setting up our various different test sets, train val, design, which is train and val together, and test just like normal. Let's fit a tree. Do we need to one-hot categorical variables before running a tree? Well, we're not going to, and let's see what happens. You can see the 5 different roof types, and here we will build our first tree where sale price is only allowed to depend on roof style. The tree will have to decide if the loss function is going to be improved by splitting on roof style. If it will, it'll have to decide how to split on roof style, what goes to the left and what goes to the right. It's only going to make a binary split. Method ANOVA, by the way, means that the loss function being minimized is mean square error. Here you can see the resulting decision tree. It's the same one that you saw in the slides. 4 kinds of roof are going to the left with an average sale price of $170,000. The hip type of roof style is going to the right, and that's got a much higher sale price. Let's allow sale price to depend not just on the roof style, but also on the living area. We've got some discussion points here. How many possible trees are there for 500 binary features? I was a bit confused in the lectures by approaching this, trying to understand how many splits could be made at each level. First 500, then 499. You saw the answer there was 2 to the power of something, and you can arrive at that by thinking carefully as to how many possible combinations of leaves can there be at the bottom. What is being done at each split? We know that we're trying to minimize the loss function at each split, and that's not a million miles away from gradient descent, as we've discussed. So, what kind of tree are we going to get here? What do you think is going to be the most important thing? Is it going to be the roof style, or is it going to be the living area? What's going on here? Let's have a look together. At the very top, you can see the first split was made on living area. If the living area is less than 1,611 square foot, we go to the left, and the price is much lower. If the living area is greater, the price is much higher. And if you carry on going down the left-hand side, you can see that it splits again. This time living area less than 1,199, and if it is less, you get $122,000. If it's more, you get $169,000, and that's compared to the other side of the tree for larger houses, where it's $241,000. Now, this should begin to set some alarm bells going. The decision tree has wanted to split by living area twice, because smaller houses are cheaper and larger houses are more expensive. But if it's split twice, why wouldn't it want to split 4 times or 8 times? Because after all, as we have seen before, there is some kind of linear relationship between living area and the price. And in order to capture that linear relationship and not just say less than 1611 or more than 1611, less than 1199 or greater than 1199, we're going to have to split lots and lots of times to get little buckets of living area. We'll discuss that a bit more, but it is a major problem in trees when a numeric feature affects the price in a linear manner over the whole of the range of the numeric feature. Let's just have a look at how we predict. So we're going to predict over the rpart object and using the whole data. I haven't actually yet split between train validation and test. These are the predictions from our first decision tree. If you remember, we only used one variable, which was the roof type. HIP was the more expensive roof type, and all the other roof types were less expensive, so unsurprisingly, this histogram only has 2 values in it. What's going to happen if we predict over our second decision tree, or if you remember we had 3 or 4 leaves at the bottom, after splitting a few times on living area and also once or twice on the different roof types? Again, not surprising, we've got 6 different buckets according to the 6 leaves of our decision tree. Let's calculate the mean absolute error. Unsurprisingly, is not a very good model. The mean absolute error for the second model, where we allowed the decision tree to use 2 features, is $38,000. You remember the semi-decent accuracy we were getting last week was something like $14,000 or better. Finally, let's make a more complicated tree. In R, this syntax over here says the sale price is allowed to depend on dot. That means everything else, every other feature in our model which isn't sale price. Let's run it and see what happens. Okay, this is a little bit messy. It's splitting at the top by overall quality. As we go down to the left, there's a whole lot of text. It looks really messy. What that says is that it's splitting by neighborhood. I don't know what those neighborhoods are, but there's a list of neighborhoods where it's going to the left, and the other ones it will be going to the right. Further down, you can see it's splitting by quality again, and then by greater living area, and then by ground floor living area, I think that is, basement square footage, and so on. So we've given it every single variable, and it's split a few times. Are you surprised about how many times it's split? Has it split not many times? A lot of times? Well, if you remember, a decision tree carries on splitting and splitting and splitting till more or less it can't stop, unless something stopped it. Something has definitely stopped this tree from getting more complicated. There were many more splits that it could make. Even overall quality, which goes from 1 to 10, whatever it is, could have been split by a sequence of binary splits into each level of overall quality. The living area could have been split many more times, and there are also many more features in our model. From memory, there are about 70 features in our model, so why didn't this tree split more times? The answer is to do with the complexity parameter. We discussed the complexity parameter briefly in the lectures. If its value is 0, you're going to get very complicated trees. If its value is 1, you're going to get trees with no split whatsoever. The default for the complexity parameter in our part is 0.1, which happens to be a pretty high setting. So let's do one last tree before we go back to our slides and see what happens if we do exactly the same thing. So sale price is allowed to depend on everything. We use all the data. The method is mean square error, so the loss function that we are minimizing each time is mean square error, but the complexity parameter is set to approximately 0. Don't worry about max surrogate, it's not important to us. And min split says the minimum number of houses that must be in each leaf in order for that leaf to be split. That itself means that at the bottom of the tree you could have leaves with just 2 or 3 observations in each one. Given that we have 2,700 houses, this should mean we could get a pretty complicated tree. Let's find out. Right, here's the tree. Can you see it? You shouldn't be able to see it. I can't see it on my screen. There are probably thousands of boxes on that tree. There's a horrendous amount of text, and the leaves at the bottom are just 2 solid rows of black lines. So that is a complicated tree. That is what happens when you grow a tree and you don't find any way to stop it becoming complicated. Let's predict on that tree. Make some predictions. We haven't yet split the data between test and train, so we can't check to see what our mean absolute error would be on test data. But what is interesting is to see how well this tree predicts on the data itself. Now, given that it's an insanely complicated tree and has the ability to completely over-predict and to take just 2 or 3 houses in a leaf, the houses in each leaf should at least be very similar over the data on which we fitted it. So it's remarkable to find in this final tree that there is a house with a sale price of $538,000 predicted at 443. That could well be actually an error in the valuation of the house, rather than a problem with the decision tree. It could also be that this is telling us that there's something very interesting about this house that we might want to look at. I have used this idea of overfitting decision trees in audits of certain datasets in order to actually find errors in the dataset. What's the performance of the tree on data it didn't see? Very simple. We'll train the tree just on the train data. And here you can see overfitting beautifully illustrated. The train error is incredibly small, $4,800 mean absolute error. That's much better than anything we achieved with our linear regression, but unsurprisingly the test error is fairly horrific, 22,000. That's much worse than our best models so far. A classic case of overfitting. Does this model have bias? You should be able to answer that. No, the model doesn't have bias. Does it have variance? Yes, it has a huge amount of variance. What can we do to think about optimizing the trade-off between bias and variance, between simple trees and ridiculously complex trees? Find some kind of way to choose the optimal complexity parameter, CV. Let's go back to the slides and see a little bit more about the complexity parameter before we come back to R a little bit later on.